This is the notes for section 9.2, exponential decay. If you haven't done so already, make sure you read the section first before continuing on with these notes. Exponential decay is really, this is just really an extension of what you did in 9.1 where we looked at exponential growth. It's just that instead of things getting bigger, they're getting smaller as the independent variable gets bigger. So basically an exponential function where we have ab to the x, just like we were looking at in 9.1, it's going to be exponential decay if b is less than 1, but yet greater than 0. Okay, so any value of b between 0 and 1, and remember we've already defined that b has to be greater than 0. So any value of b between 0 and 1 would represent exponential decay. Okay, as x increases in those cases, the value of the function decreases. Okay. Examples of exponential decay that we'll be looking at either through our problem set or through these notes include depreciation, half-life, and radioactive decay. All of those are examples of exponential decay. Alright, I'd like to now take you through an example of the different types of exponential decay that we might run into in this course. First of all, we're looking at depreciation. When we talk about depreciation, basically that's just the decrease in value of manufactured goods over time. Okay, so let's take a look at example 1 here. It says, suppose a new piano costs $8,500 and depreciates 6% each year. Write an equation that gives the piano's value after t years, or when it's t years old. And the key is that we want our equation to represent the value of that piano. Okay, not how much it's depreciated, but what is its value. So I'm going to say, and I'm going to call my function f. So I'm going to say f of, okay, and remember we want it to be ab to the t then. So a represents what it started at, which is $8,500. B represents the growth, or in this case the decay rate. Well, if it's depreciating at 6%, that means each year it's only holding 94% of its value. So my growth rate is 0.94, which is actually a decay. Okay, anything between 0 and 1. So that would be the value that I'm going to raise to the t power. So that would represent the equation I'm looking for there. And then part B here, if I want to find the value of that after 5 years, I'm really finding f of 5. And then I'm going to go to my calculator and figure out what that value would be. So I'm going to write that down. F of 5 is 6238.18. So the second type of problem that I'd like to look at is problems involving half-life and radioactive decay. Half-life, we define that as the amount of time it takes for half of the atoms in a substance to decay into another matter. Okay? So here's an example that we're going to go through. The thing that we want to think about with half-life is that our growth rate is always going to be 0.5. It's always going to be half. Strontium-90 has a half-life of 29 years. This means that 29-year periods, half of the strontium-90 decays and half remains. Suppose you start with 1,000 grams of strontium-90. How many grams remain after 6 half-life periods? So what we want to do is we want to just kind of fill in this chart. So after one half-life period, okay, if you think about this now, if it started out with 1,000, after one half-life period, it's going to have to go down to 500, or half of that value. And then after each successive one after that is going to be half of the previous one. Okay, so really what's happening is we're dealing with a recursive formula. We're always taking half of the previous value. Now these, remember that n represents the number of half-life periods. It does not represent the number of years. So in part B it says, well, how many years is 6 half-life periods? Well, if each half-life period is 29 years, okay, so we know that each half-life period is 29 years. Therefore, to find out the number of years that would be, we're going to take 6 times 29 to get that value. If I multiply that on my calculator, then 6 times 29, that would be 174, so it would represent 174 years. Okay, part C then says, write a recursive formula for A sub n, the number of grams that remain after n half-life periods. So n represents the number of half-life periods. We want to write a recursive formula for that. So to write that recursively, we're going to put A sub 1 being 500, because that would be the amount after the first half-life period. Now, sometimes you'll see the book will put A sub 0 here and make it 1000. We can work with that. Okay, it's going to be the same thing, but I'm trying to be consistent with what we did when we first were looking at geometric sequences. So if A sub 1 is 500, then A sub n is equal to, well, each half-life period, half of the particles remain, so that my ratio between terms is 1/2, so it's going to be 1/2 times the previous term, A sub n minus 1, and that's for n values that are greater than or equal to 2. Okay? So that's our recursive formula. And then part D says, well, let's write it explicitly. And here when I'm going to write it, I'm actually going to do it. I'm going to set mine up so that n is greater than 0. If I set it up in such a way that n is greater than 0, then I can have my starting value be that 1000. Okay? Just like I said, we could actually do over here recursively as well. So I could have my starting value be 1000, and then if I did that, instead of n minus 1 here, I would just have n, because n has to be greater than or equal to 0, so that's why we could have that way. So this would be an explicit way of writing that. Okay, and then part E says write a formula for the number of particles remaining after any real number of half-life periods x. So if I'm going to write that as a function, I can say f of x is equal to the starting amount, 1000, times 1/2 raised to the x power. Okay, so that here's my starting value, and here for half-life the growth rate is 1/2. That's the thing that we really have to remember about half-life, is that growth rate will be 1/2.